Testing 1 2. Testing 1 2. 1 2 1 2. Testing 1 2. The live stream. Broadcasting the live stream. Broadcasting the live stream. Testing. Can anybody hear me out there in internet land? 1 2. 1 2 1 2. Testing. 1 2. Oh, we have a picture streaming online. Oh, there's my voice. Yep.
Someone says they can't see the live stream. Let me ask.
Okay, all right. 1, 2.
Neil?
Yes.
Everyone, thank you very much for your patience. I'm sorry to take this long technical difficulties. As usual, I think the Cyberspectrum way now. It's been established that way. But hopefully you enjoyed the extra pizza. Let's rock and roll.
Okay, good evening, everyone. My name is Neil. Thank you very much for coming tonight. I would like to welcome you to the 19th Cyberspectrum meetup. Tonight's meetup, 19. That's almost 2 years. I can't believe it. 19. Today's event is a special edition of Cyberspectrum held during the week of the GNURadio conference here at the University of Colorado at Boulder. This event series serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your hardware or software background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event here tonight is being sponsored by Bastille Networks and is being hosted by the University of Colorado at Boulder. We'll begin the evening with a short announcement from NewTAC regarding their LTE workshop series. Our first speaker will be Alex Chemeris from Fairwaves, who will give a talk about their new tiny SDR radio solutions. Our second speaker will be Jared Boone. Sorry. Out of order here. Let me... Okay. Our second speaker will be Jared Boone, who will give a talk titled SDR Polyamory. Jared will discuss non-GNURadio approaches to doing signal reverse engineering, prototyping, testing, and transmitting. Our third speaker will be Martin Brown. Where's Martin? Martin Brown, who will give a talk titled SDR is hard, but installing GNURadio is not. Bootstrapping your bench with PyBOMBs and CGRAN. Martin will show us how to use PyBOMBs to get a setup running on most systems without effort, even for cross-compile setups. Our fourth speaker will be Chris Kuth, who will give a talk titled Disposable, Stealthy, Cheap SIGINT. Chris will discuss some observations and considerations for using inexpensive and compact ARM boards for signal analysis. Our fifth speaker will be Sylvain TNT Munot, who will give a talk titled Quick Introduction to the Receiving the Thuria and MECSAT satellite phone systems. He will provide a quick introduction to GMR itself and then discuss the Osmocom GMR project and how to get started using it. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The videos for all the previous Cyberspectrum events have already been posted. We have set up a channel on IRC on Freenode called #Cyberspectrum as a way for people remotely watching the live stream to contact the local group here with any comments or questions, as well as to alert us to any audio-visual problems. Future meetup locations will return to the Bay Area and will continue to alternate every month between Noisebridge in San Francisco and the Edis Research Office in Santa Clara. Tentatively, the next meetup will be held on Wednesday, October 5, at the Edis Research Office in Santa Clara. Further details will be posted on the meetup page about 1 or 2 weeks prior to the event, so please tune in, pun intended, including to see a list of speakers and presentation topics. As always, if you'd like to present something or if you have any ideas about future topics, please let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would like to thank Bastille Networks for providing complimentary pizza and soda. We would like to give a big thank you to University of Colorado at Boulder for providing the space and hosting the meetup, and specifically to Ken Baker, Dirk Grunwald, Therese Manley, and John Kelly. Without all of their help, the event here tonight would not have been possible. And with that, we'll now get started. Thank you.
Finally, yes.
Thank you very much, Neil. Let's get right to it then. Yeah, that's the one trick. You have to wear 2 wireless mics, one for the PA here and one for everyone out there.
I think just right here. hopefully your thing reaches, your cord reaches. Yeah.
Alex, you add me on Hangouts?
Not sure.
Sorry, you're on Gmail, right?
Yes.
Okay, so just add me, Violin256 Gmail, and then I can put you.
I'm just going to take this out, Paul. Take this out.
talk?
Hello, hello.
Yep, yep. That's good. One,
Okay.
two.
What's happening?
If you're mirroring, just share your whole screen at the moment. And I think that'll be the best way to do it. Okay.
Works.
Thank you, Alex. Take it away.
Sorry, guys. Okay. So I promised this to be a very quick talk. So
As long as it's slightly longer than the setup time, it's all right.
I want to talk about a software-defined radio, which I'm trying to find in my pocket, because it's software-defined radio which not only fits a pocket, which you can actually lose in your pocket. So I guess you can't really see it from here, from there, right? But you can see it on the screen. So it's a really tiny software-defined radio. And your next software-defined radio should be tiny, because that's where we are going. So this is software-defined radio. You probably saw it today during my presentation at the GNURadio conference briefly, but just a little bit more detail. So it's a small size. It's designed to be embedded friendly. So you can put it into real embedded applications because we are, in Fairwaves as a company, we do a lot of work with base stations, cellular base stations, designing full GSM and LTE base stations. So we need something which can be embedded and work with the wide temperature ranges, et cetera, et cetera. So we designed this specifically for ourselves, but we do want to share it with everyone and make sure everyone else can have the same fun. So the board is, again, designed primarily for cellular applications. So that's why I say here it's targeting LTE and then 5G, but it's still SDR. So whatever you can do with this is up to you. And the goal is that with all the performance and size and like industrialness of this board, we want to make it very, very inexpensive and affordable for everyone. So we want to target everyone starting from hobbyists to IoT projects to amateur professionals to embedded systems and all the way up to research labs. It sounds like a very wide range of users, but we think it's doable with this. So the radio heart of the board is Lime Microsystems LMS 7000 chip, which offers you 100 kilohertz to 3.8 gigahertz of tuning range. The ADCs is running 160 megahertz, so it's a very, very wide band. And the good thing is that because it's a PCI Express, you actually can get this data into your computer at very, very low latency. So like there are other other SDRs which also have a wideband radio front ends, but you can't access this data because they typically run USB 3, and USB 3 is just not good enough for this. And but there's a typo here. The RF modulation is up to 160 megahertz. So PCI Express is widespread in very low latency. So again, I'm not sure how much of you followed the presentations today by Epic Solutions, who also have a mini PCI Express board. But the interesting thing is that with mini PCI Express latencies, you actually can work with CSMA protocols, meaning like Wi-Fi, for example, where you have a very strict timing requirements between sensing what's going in the air and actually transmitting something. Again, it's not possible with USB, for example. Why mini PCI Express? It's very widely available in multiple, in many single board computers. It's available in laptops. There are even ARM boards with mini PCI Express. So what is interesting here is that, again, because we are coming from cellular world, we paid a lot of attention to the clocking. So the board has a built-in GPS DO. It has a very quite like a T6CO, which is very stable for T6CO. If I remember correctly, it's a 200 ppb plus GPS DO, so you can get it to a single-digit ppbs if you have a GPS signal, which is like requirement for cellular systems. That's where we are coming from. And we also have connectors to synchronize multiple of these boards clockwise, in terms of clock. So you can build massive MIMO systems using this board. Just some views. So I was surprised to see that there are actually ARM boards with PCI Express bus. I was always thinking that PCI Express is like a x86 territory. Turns out not exactly. If you're looking for something really small and power efficient, then you can go into ARM. And again, I think today was a presentation about using NVIDIA Tegra for speed optimization, right? And this chip also has PCI Express. So you can have X-Trix on Tegra with CUDA optimization. So again, there are plenty of x86 embedded platforms for this board, with the mini PCI Express. So what's interesting is that Thunderbolt actually has ability to talk to PCI Express, and this is how we are developing this board. So like Sergey is sitting there, who is our primary developer of X-Trix, has a laptop which has Thunderbolt, so we connect this to Thunderbolt, and we connect this to a laptop externally. It's very convenient. Also has very low latency, unlike USB. And with PCI Express, you can have multiple of them on the same carrier board. So Thunderbolt 3 is in the latest Intel chipset, so it should be very available. So if you want to plug this into a desktop computer, there are passive converters from mini PCI Express to PCI Express on eBay and Alibaba, available for like $10. So you can plug this into your desktop computer, for example, or your small embedded server which has a full-size PCI Express. So we'll probably look at something like PCI aggregation carrier board, which will have multiple slots, and you can slot multiple Xtrixes on the same carrier board to have like up to 64 by 64 MIMO on the same PCI Express board. So the status of this board is that these are first prototypes we have. We are opening an early access program right now for selected partners who will get access to the next round of prototypes. And if you're interested, please contact us. Otherwise, this board will be available sometimes next year. I can give promises about exact timelines at this point. If you want if you are interested in general and just want to follow us, then go to xtrx.io. That's the blog where we are posting progress on this board. Subscribe to the news and follow us on Twitter, where we are also posting the progress. That's it for this presentation. Hope it was short enough. If you have questions, you can grab me after the event, I guess. Thank you.
Thank you, Alex. Any questions for Alex? Yeah. Can I?
It is on. Okay. Your slide said something about 60 megahertz RF modulation bandwidth, and I thought I heard you say that that was a typo.
Yeah.
But I've seen that specification elsewhere for the LMS 7000 in multiple places, and I've been confused by it. And is there a story behind that?
Well, I'm just not sure how much I can say on the recording. But it will be more than 100 megahertz. So
Okay, I'm wondering, how do you access this chip? Is there a Linux kernel driver or something for it?
Oh, okay. So basically, yeah. So we wrote our own kernel driver to access basically to implement the DMA and PCI Express. But to work with actual chips, there is a library called libl-ms7. It's just a C library which has functions to control the chip itself. You supply it with callbacks to access the actual physical chip, and you're using this. So basically, our architecture is that we have an FPGA code which implements PCI Express. We have a kernel driver which talks to our FPGA code, right? Then we have a user space library which abstracts all the guts of the PCI Express and kernel stuff, and implements a high-level API like tune, get samples, things like this. And we will also have a wrapper, a UHD module. So if you're, UHD is a driver which is developed by Ethos Research for users, but it became so widespread. It has a module support where you can get your own hardware, and basically Xtrix will expose UHD API, and each software which works with UHD will be also supported by Xtrix this way.
Okay, thanks.
That's.
So I've been looking into Thunderbolt to PCI Express adapters. Are you planning to make your own, or is there some commercial product? Because most of them that I've seen actually are for full-size PCI Express cards and kind of more expensive than my laptop.
Sorry, which converters?
Sorry?
You asking about
A Thunderbolt to PCI Express adapter that you kind of.
Oh, Thunderbolt to PCI Express. We were able to find one which is So there are, basically you can buy some development boards for something like $300.
Mm-hmm.
So we are looking into creating our own, which would be cheaper, but
Awesome.
well, more volume, less margin, making margin on something else. I don't know. Like, we are still looking at this.
Yeah, well, thanks.
Right now we have we will release soon an adapter for full-size PCI Express with the built-in LNA and preamps. So you will be able to have like a good like 100 milliwatt output power on all the whole bandwidth.
Do you mind if he hooks up his laptop while you're...
Sure. But
By all means, feel free to finish your thought.
sure. Yeah, I'm saying that we have a multiple of adapters in mind. So Thunderbolt, like PCI Express with multiple boards, but we don't like share. I mean, we don't have the specific timelines for this yet. The one which we have right now in works, which should be manufactured next week, is the one which is pretty much the same passive board as you've seen, but with LNAs and preamps.
Cool, thanks.
All right. Round of applause for Alex. Thank you.
And now we're going to transition directly to our next speaker, Jared Boone. And remember that his Twitter handle is the very catchy ShareBrained. And he's going to take us through some non-GNURadio approaches for doing signal reverse engineering, prototyping, testing, and transmitting. Are you all mic'd up?
Almost. Is this the active one? Stereo.
And what's on the second round going to live stream? Is that cool?
That is cool. That's a microphone, huh?
Yeah, it's a bit deceiving when you see it first time.
Yeah.
Can anybody hear that weird sound? Yeah. Anybody got any theories? I thought it was somebody blowing into the recorder without actually knowing how to play it.
Does anyone know how to play one?
All set?
All set.
All right, round of applause. Thank you, Jared.
Thank you.
Take it away.
So my name is Jared Boone. I have a little company called ShareBrain Technology that makes an add-on for the HackRF software-defined radio that makes it entirely portable, so you don't need to plug it into a computer. I'm involved in HackRF in the PortaPack because I have an interest in wireless security. Oh, sorry, I probably shouldn't move around too much.
No, that's all right. You do your thing.
Okay.
Scrap you.
Yeah, so I'm
Professional outfit. I mean, isn't that obvious?
right. Well, yeah, so I'm interested in wireless security and privacy, and have spent a lot of time, of course, with GNURadio. And I thought, okay, so I'm coming to my first GNURadio conference, and I'm going to give a talk at Cyberspectrum. What can I talk about that people aren't going to already know everything about? So I'm going to talk about not GNURadio. In particular, I'm going to talk about how I usually reverse engineer things like tire pressure monitors,
ham radio protocol. I mean, ham radio protocols you don't have to really reverse engineer, I suppose. But, well, you know, yeah, so various more simple signals, not like OFDM, LTE type stuff. And just talk about the workflow that I use, which isn't really conducive to GNURadio, because GNURadio is much more about stream processing and building up a filter or a flow graph that will process samples coming in one side and smoothly comes out the other side. If you've got packets that you've captured and you don't know what they are and you want to tease them apart, GNURadio isn't necessarily the fastest and simplest way to do this type of stuff. So I am going to, you'll notice I have no slides on the screen, and that's because I'm going to go 100% demo, as Dominic calls it.
Hey, can you give us a thumbs up?
Okay, so to start with, of course, we need to get an interesting signal. And you know, there's several ways via the command line to do that. I'm using a HackRF, so there's good old HackRF transfer, which has got a bunch of different options, of course. Unfortunately, unless you really know what you're looking for, this is kind of a pain in the butt. So there are tools like, first of all, just recently put together by Dominic and Mike Walters, a modification to Q-Spectrum Analyzer, which uses the HackRF to quickly retune across a bandwidth far greater than its native sampling rate. So ordinarily, you know, HackRF does about 20 megasamples a second. Using Q-Spectrum Analyzer, you can do a whole lot more than that. You can sweep pretty much the whole 6 gig range of the HackRF. Let me get it here on screen. I was looking for some interesting signals earlier on, and I managed to find them. There's this interesting peak right here, kind of suspicious. I think maybe we'll check that thing out later. But yeah, so I can go and stop this. I can set it to, you know, 6 gigahertz if I want, and away it goes. What's that? No, I mean, I'm just showing, hey, it in fact works. So yeah, we've got Q-Spectrum. It's very, very new. So right now it requires modifications to the HackRF firmware in order to do very, very rapid retuning. I don't know exactly how fast, but I'm guessing it's on the order of a few hundred microseconds. Dominic? Yes? Okay. Yeah. Faster than you can do by initiating that process over USB, because of course USB's got a latency in going back and forth of, you know, a millisecond or more at best. So yeah, you need modified HackRF firmware, and I expect it'll probably wind up in the released HackRF firmware at some point. And then Q-Spectrum Analyzer had to be modified a bit in order to accept HackRF samples. So that's cool. I'm also a fan of, okay, so technically I guess there is GNURadio in here. But if you're not using GR or Osmocom FFT with the Phosphor add-on, you're really missing out. This uses the GPU in order to accelerate FFTs and display in a waterfall. So again, I'm going to head to about 215 megahertz because there's that weird signal. It really doesn't fit very well on this very small or very low resolution. But yeah, so we've got a funny little signal here at, what, 215.2? Yeah, something like that. If I tune up to, say, 910 megahertz, we probably see a lot of, oh, here we go. There's not a lot going on here either. I guess we're kind of in a bit of a Faraday cage with this metal wall on all sides. How about LTE? Yeah, there's some cellular. So yeah, if you're not using this, you definitely ought to check it out. It's a great way to catch very fast signals. You know, GNURadio's got these WX and QT waterfalls, but they tend to have a lot of cracks. So you'll have a very fast event that comes through, but because it doesn't happen to fall into one of the FFT windows, you won't see it. On the other hand, Osmocom FFT catches pretty much everything. So let me capture that signal around 215 megahertz here. I'm going to use HackRF transfer, amplifier off, set the gains kind of low. sample at 10 megahertz. Oop. Where am I? There I am. 215, 23123. Oops, I'm missing an argument. What am I missing? Do I? Oh, yeah, I do. Good catch. Something about the way my screen is wrapping. Okay, so I'm recording this signal around 215 megahertz. I'm going to stop it, and now I've got a capture file saved on my disk. I'm going to make use of that here in a moment. I'm going to look at it in Spectrum. So I captured, has anyone here used Spectrum yet? It's more people than I expected. Okay, well, that's cool. Yeah, so Mike Walters, who also was part of the Q-Spectrum Analyzer enhancement, has created something kind of like Baudline, except open source. And already that's been paying a lot of dividends in that there's a lot of contributions that have gone into it from I don't know, at least half a dozen people have added code to it. And it's starting to become a very useful tool. So I want to look at that signal that I just captured using Spectrum. I'm going to tell it what sampling rate, -R, what sampling rate I recorded the capture file at, and then I'm going to point out that the file that I want to open, and there we go. It's a little bit different than Baudline in that it uses a horizontal display, which I think, with all of our wider screens these days is probably the better choice. But you can scroll back and forth very smoothly. It'll open up files, I think technically well above 4 gigs, but I think there's a couple of bugs still outstanding that kind of screw that up. In any case, it's very responsive. Let's check out this signal a little bit by increasing the size of the FFT and figure out what kind of signal we might be dealing with. It looks like it's analog. Whoa. It looks like it might be a narrowband FM signal. So that's useful, and it's offset about 200 kilohertz above the frequency that I was tuned to. So at this point, I'm going to show you another tool that is called CSDR. I've got the GitHub page here for CSDR somewhere. Yeah. So it's a C-based software-defined radio toolkit that is designed to work using Unix pipes. So you can assemble a signal processing chain by taking your source file and then piping it through a sequence of processing blocks, not unlike GNURadio, but you can build it up very quickly in the command line. And of course, also share it very easily by just pasting it into a paste bin or something like that. So I'm going to concatenate the file that I captured, and then I'm going to run it into CSDR. And first of all, because I captured this file using the HackRF format of 2 signed 8-bit integers as a complex pair, I need to convert it to floating point so that the rest of the blocks can work with it. Oops, S8. There we go. And then, because the signal is so much narrower than the sample rate, I'm going to decimate it a whole bunch. So CSDR again, FIR decimate, complex to complex, and I'm going to decimate it by 40. Yeah, and I'm going to use the Hamming window. And then, because it looks like it's narrowband FM, I'm going to use CSDR again to FM demodulate. And then I'm going to pipe that into just an output file. And runs very quickly. I now have an output file. I can open that up in Audacity. I just cannot type. There we are. OK. Ooh, Audacity looks really crushed into this screen. OK, output.f32. So Audacity is a tool that I wasn't actually planning to talk about, but I should mention it as sort of my go-to for looking at capture files that are not complex, but just some sort of a time domain signal. Unfortunately, we don't have a better tool for doing this yet, although I think Spectrum at some point should have the ability to look at just real-only sample files. Now I'm trying to remember what my sampling rate is. I decimated by 40, and I was sampling it, oh, so 250 kilohertz. Yeah. So let's zoom in and see what we've got. Oh, I did, didn't I? Oops. Okay. Okay, well, let's just assume. Maybe Audacity's being weird to me. Okay. Well, let's just go based on the assumption that it's an audio signal, because what narrowband FM signal isn't audio, or at least listenable as audio? So I'm going to use CSDR to do a fractional decimation. I'm going to decimate by, oh no, wait, by 5.208, so I can get it to a nice round 48 kilohertz. And then I'm going to do a de-emphasis. Using the US de-emphasis. And then I'm going to run it out through the SOX play command. Oops, there we are. Oops. Oh. That didn't sound right. Oh, you know what I forgot to do? So remember that the file was offset by 200 kilohertz from the frequency that I was tuned to? I need to to mix the spectrum down 200 kilohertz so that it's in the center. So that is done with CSDR. Shift table, complex. Oh, yep, got me. So that's the downside to command lines. If you don't type well, you'll screw yourself every time. Let's see, so it was 200 kilohertz down. So one of the funny things about CSDR is because it's all pipe-based, they're not passing any metadata from block to block. And so the commands down the pipe don't know what your sampling rate is, and you specify everything in fractional sampling rates. So I have to figure out, okay, 200 kilohertz into 10 megahertz is 0.02. So I want to tune down 0.02. Sounds like me talking.
Yay!
It wasn't very loud. Oh, well. Yeah, okay, so you can do narrowband, or you can receive wireless microphones with CSDR pretty easily. That's, pretty clear, easy to understand incantation, I think, if you've got some basic SDR background. Well, certainly if you've got GNU-Radio experience.
I like the quadri the best. That's what gets me.
The which one? Oh, quadri, yeah. I think that, I'm just guessing from the surname, that Simonis, Hungarian, okay. Yeah, so we've done analog signals. What can we do with digital signals? So I have a capture file that was sent to me by somebody in France that they were interested in finding out or learning more about some of the packets that they'd captured on a particular frequency. So I'm going to do pretty much the same thing with CSDR. In this case, I didn't use the HackRF transfer utility. I used the PortaPack capture feature. So the PortaPack has a SD card slot, and as you're walking around, you can hit record, and you can record either demodulated audio, AM or FM, or you can also record 500 kilohertz worth of spectrum, just raw, right onto the SD card. And so that's what this is here, is it's a file that someone sent me that they captured using their PortaPack. But the capture files are in complex int16s. So I've got to use a different convert command to convert those to float. So let's see. Actually, let's first look at it in spectrum. Getting a little ahead of myself. So the sample rate was 500 kilohertz. And there it is. I wish it would maximize. Okay. So here we've got a bunch of packets. This one looks kind of interesting. So let's try and pick that one out and try and recover data from it. So one way to do that is to use in Spectrum directly. You know, I can go and find a packet that's interesting, zoom in on it. Let's see. I've got a special little feature on my version of InSpectrum that has this. It basically allows you to sort of focus up the transform to bring the bits out a little bit better. So let's mess with this packet a little bit. So it looks like it's on-off keying. InSpectrum provides a way to convert what you're seeing in the spectrum or the waterfall view to amplitude. And you get this little window that you can drag over and widen up. And can I even get down here and see? Yeah, there it is. It's pretty, yeah, so you can see it there at the bottom. We've got essentially an amplitude representation of that particular signal. From there, you can add another plot which will threshold that and turn it into what looks like, oh, I can't cross my boundary. This is not working well. This works better for FSK. In any case, you would see a much squarer example of the same amplitude graph down here. And let me go find an FSK one because they work better. Oh, that's okay. Ah, that looks like FSK. Okay, so now we'll zoom in on that guy. The zoom feature still needs a little bit of help. Doesn't actually center on what you're after. Okay, so now let's go and add a derived frequency plot. Oh, it occurs to me if I turn down the FFT size, I'll have more room on the screen. Okay, so we'll add a frequency plot, do the same deal here, enlarge it to encompass both lobes, and now we have something that looks a lot like a square wave. It's kind of noisy. We can pull it down and kind of get some of the noise to go away. And then can right-click and say, give me a sample plot. Oh, wait. Drat. I've clicked on the wrong one. Add threshold plot. Yes. Okay, so now we've got a plot down here, which looks very much like a nice square wave, like we're really getting the bits back out of the packet. You can right-click on that. Uh-oh. Oh. You can then turn on the enable cursors and line up your individual symbols. Crank the sucker up for however many symbols you've got. Get the thing lined up with the edges. And then right-click and say extract symbols. And if you go back over to the console from which you ran it, you get bits out. And you can paste those into whatever tool you use to reverse engineer packets and get on with things. However, that only gets you one packet at a time. So obviously it's a lot of manual effort. So I've, in combination with CSDR, I've devised a couple of additional tools that do the clock recovery and symbol search so you can get a bunch of packets dumped all at once. And let me show you what that looks like. First I start with my capture file, run it through CSDR, converting it to the right sample format. I'll decimate. What's that? Decimate it down a bit. And then I've got this tool called OOK Clock Recovery. So the earlier packet that we were looking at that I wasn't able to get bits out of, we can get them out with this tool. I happen to measure the symbol rate at that time as being 8.192 kilohertz. So now I've got bits that have been retimed. So I've got one bit per, or one sample per symbol. And I can run that into a symbol search command and look for a preamble that I happen to know looks like that. And I get packets out. So yeah, pretty easy once you've found all these different parameters using in Spectrum. You can also, another approach is, well, I won't go there. When did I start? Didn't even look. Okay. So to do an FSK signal, you do something similar, but instead you go back a bunch. FSK, of course, it's much more important that you have your signal centered around 0 hertz so that you can do, if you're not doing some sort of a frequency correction, you need to go and slide that around 0 so you get a nice baseband signal out that you can then run through clock recovery. So I happen to know I'm after a signal measured via in Spectrum that is offset a certain amount from DC.
Sorry, just a request. Apparently the speaker at the back stopped working. I don't know whether that's a technical glitch or not, but can you tap your mic just to see if...
Tap, 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 tap.
The transmitter's the one?
Red light on both.
That one.
I've got a red light on both of them.
That's fine. The one on your right is fine. The one on your left is the one.
Battery light just went off. Not sure what that means. You want to take a... Sure.
Is it out of juice?
The battery light was on when I looked down at it. But I don't know, sometimes that means it's good. Sometimes it means it's bad.
I don't know, Nate, what's the deal? Huh? Basically, maybe just project.
Okay. So leave this off. I guess there's, oh, now it's back on again. Interesting. Okay, so doing FSK. The important thing with FSK is...
Yeah, it's not working, so you just have to talk about it.
Okay. I'm not sure I have much more in me, but I will give it a shot. So yeah, with FSK, you've got, if you're going to do clock recovery, you want a signal that is centered around DC. So I'm going to go and do I'm going to mix with a complex sinusoid, shift the spectrum down a bit, and then run it through the FM demodulator. And then I've got a baseband clock recovery tool. Baseband clock recovery, that's better. 500 kilohertz. And symbol rate of the packets that I was finding was 19,200. And then I'll use the same symbol search to find pattern that looks like this. And on and on. And then, what is it, 6 zeros? 6 zeros. And it grinds away for a bit, and once again, I get packets. Come on, I know there's 2 more in there. There we go, 3 more. All right, cool. So I was also, earlier today when we were in the vendor area, I captured a mystery signal, and I'm kind of curious what it is. People were talking about it as if it might be like a utility meter signal, but I haven't quite figured it out yet. So I'm going to put it up on the screen, and I know there are a couple of people here who are experienced looking at utility meter packets and stuff, and hoping to maybe get a little bit of insight into what's going on here. Let's see, what is today, the 15th? Yep. Okay, so first of all, I see there's some sort of frequency hopping, a lot of small packets going on up and down throughout the spectrum. And so let's grab this guy right here. Definitely looks like FSK, because we can see it's got a little bit of a serrated edge, and it's moving up and down between two frequencies. I'm going to zoom in on it a little bit and try to figure out what the symbol rate might be. Ooh, I really zoomed in too far. Okay. That's better. Okay. Oop. So like before, I'm going to add a frequency plot. And I'm going to bring it down here onto this guy and have a look at it. I may be, yeah, it's a little noisy, but it looks like it's workable. And then try and line up the grid here and figure out what the symbol rate is. That looks to be about right. So 9600 baud. Okay, so we got our symbol rate. Let's get that signal down to around DC and decimate it a little bit and do the same process over again. So I'm going to cat that file. Been about half an hour. Okay. You know, this is pretty much a rehash of the last thing I did. I'm instead going to move on to talking about using let's see, where is it? IPython notebook to synthesize signals. So a lot of times when I'm developing a demodulator for the PortaPack, I need to test it with some sample signals. And historically, I've just, like for instance, when I was doing the AIS boat transponder monitoring demodulator, I would just set up the radio, put up the antenna, and receive boats in the area. And of course, boats come and go during the day, and there aren't a whole lot of people sailing around late at night, and I usually work late at night. So it's not really a very good test. So I'm trying to get more disciplined about testing things properly. And one approach to doing that is to just synthesize your own signals to begin with. And I like to use Python to do that. So I'm going to start up Jupyter Notebook, which is the renamed IPython notebook. It'll pop up here in a browser. Oh, except I'm in the wrong directory. Yeah. There we are. And go into my IPython notebook and just quickly go through the approach that I use in order to synthesize, and also to test my algorithms before I actually bother coding them up in basically ARM assembly language. I like to work out the algorithms in Python as best I can to make sure I'm not barking up the wrong tree. So to start with, I built a bunch of helper functions that just manipulate strings of ones and zeros, the symbols that I'm going to use to construct my example packet. I've got an NRZI encoder and decoder, et cetera, et cetera, et cetera. And then down here, I use all of those to essentially build an AIS packet, complete with the training sequence on the very front of the packet, the end of packet. AIS is interesting in that it's got a marker for the end of the packet as well. And then go through the process of concatenating all that stuff together, and now I've got a symbol stream of zeros and ones. Then to modulate it, I go and turn it into a bipolar signal, turning zeros into negative ones and keeping ones as they are. And then I do a bunch of signal processing where I essentially run the signals through I create a Gaussian pulse filter because this is a GMSK signal, and convolve that against the sample stream, and I wind up getting out, a nice quadrature signal that I can then signal process using my proposed algorithm to go the other direction. So, here's the code where I go the other direction. I go and mix the signal with a complex sinusoid in order to create a matched filter and do sort of the typical stuff you might do in GNURadio. But I feel like this allows me a lot more control than GNURadio often does, and allows me to also do a lot of static plots in line, which I find much more helpful. There also isn't just the kind of compile loop. GNURadio starts kind of slowly on my system, and I think it's probably just an artifact of the fact that the thing's almost 6 years old at this point. But this feels like a much more smooth flow for actually testing things before I implement them in code. Now, in the process of reverse engineering, once you've got a bunch of packets, sometimes you need to be able to do statistical analysis on those packets to figure out what's in them. So I've done a lot of work on tire pressure monitors that are on cars, and have done a couple of projects that, to varying degrees, have attempted to produce a decoder ring for all of the different tire pressure monitors out there. So one of the tools that I have, which is in my TPMS project, my username on GitHub is jboone, J-B-O-O-N-E, is a program called Packet Stats, which just allows you to run a list of, or basically a text file full of packets that are just ones and zeros into Packet Stats in order to evaluate the distribution of zeros and ones at every position within the packet. And I find this most useful for identifying, say, where a unique identifier might be for the particular transponder that I'm receiving, or where there might be a checksum. In the case of a checksum or a CRC, usually you find a row of 8, 16, 32 bits that have a very even distribution across a lot of packets, because a checksum should be kind of noisy. And in this particular case, I find at the very end of the packet, sure enough, 72 to 79 are almost exactly 50% zeros and 50% ones across all of the different packets that I've evaluated. So that's a tool I find very useful. Then, let's say you figure out where the CRC or checksum is in your packet. How do you figure out what the actual CRC polynomial is? There's a great tool called, I've got it up here, brute force CRC, which for smaller CRCs basically just goes through and tries every one. And when it finds one that works for all of the different packets that you fed it, prints out the polynomial and whether you reverse the bits going in and going out, all these other things. So let me show you how that works in practice. I've got the same file before. These are packets from a bunch of tire pressure monitors that I just collected from the side of a road in Portland. And I'm going to pick only packets that I've seen at least 3 times, so that I know I've got at least 3, for every unique packet that I've received, I've got at least 3 copies, and I know that they're not noisy. You want to weed out any packets that have got error bits in them, because they're obviously not going to pass the CRC. So I'm going to take only ones that have at least 3 occurrences of the same unique packet, and I'm going to pipe that out into another file. And then I'm going to cat that file into, nope. Already did that step. I'm going to cat that, or I'm going to feed that to brute force CRC. So file tpms 80 bin common text. And I'm going to tell it, start at the very beginning of the packet to compute the checksum, and go for, these packets are 80 bits long, and go to the 72nd bit. So basically I'm saying the payload is from 0 to 71 bits. And then evaluate or test, assume the offset is at bit 72, and it goes for 8 bits. I'll clear my screen. Woo! Oh, yeah, I cannot type. There we go. So it goes and tries a whole bunch of different stuff, and it finds, hey, there's a polynomial and an initial value for the CRC calculation, and if I were to use this, I would be able to validate new packets that I receive for the same type of tire pressure monitor and know that the CRC is correct or not. So I want to show one more thing, which is just synthesizing signals with just straight Python. It's more of a just sort of a fun hack that I did at DEF CON that is an example of using Python to create a baseband file that you can transmit. So I was at DEF CON last year and kept walking by the scavenger hunt table, and they had this really awesome boombox on the table. And you'll see why here in a second as soon as I find the photo. It had a built-in black and white TV. And they brought along a bunch of NTSC encoders and were transmitting a little sort of hacker video loop that they'd put together. And I kept thinking, I want to put my own image on that thing. So I was talking to my friend Peter, and he was totally egging me on. And I spent a bit of time with the NTSC spec, which is from 1993, or 1953, sorry. Where is it? Yeah, a little big difference. There it is. Any of you who've played with NTSC, this is totally going to look familiar. You've got all these front porches and back porches and chroma bursts and all that stuff. But it's basically, at the end of the day, it's just an amplitude modulated signal. So it should be really easy to synthesize, right? So let's have a look. What did I call it? Synth. Yeah. Whoops. No, this is fine. Blow it up a little bit. So yeah, I essentially decided to implement it by just going with all the parameters in the spec and using all the exact time values, picking a sampling rate that happened to be very amenable to doing things like color bursts. So if you're doing color on NTSC, you need, and you wanted, if you're doing color on NTSC, you need to deal with the 3.58 megahertz color burst. And I thought, okay, so eventually I'm going to do color. Maybe I'm just going to start out black and white because this TV at DEF CON is only black and white. But I'm going to pick a sample rate of 14.3 megahertz because it'll make doing color down the road a whole lot easier. So a lot of the numbers and stuff you see in here are kind of biased towards that. But essentially what I'm doing is computing an array of values for a horizontal line that look exactly like that PDF that I showed you of the NTSC signal with the vertical sync pulse and the horizontal sync pulse and the front porch and back porch and all that stuff. And then I just produce a whole bunch of them and concatenate them together and shoot them out to a file that I can then play back with HackRF transfer. So let me do that. Does anyone have a black and white TV?
I have a GNU radio.
No, GNU radio. I have a black and white television that I bought off of eBay for 9.99 cents. So yeah, this is the Sony Watchman, and there's a black and white CRT shoved in here. It's flat, so it's not square, and then they've got a mirror with a little angle to it that kind of undistorts the horrible thing that they did to the CRT to get it in here.
What's the battery life?
I haven't run out of batteries yet, but I only got it a few weeks ago, and I haven't been using it that much. Purportedly, on eBay, yeah, there's a few out there still, although they're not as cheap as this one. Right, sure. Yeah, well, this one had a broken VHF, UHF switch, but I'm totally going to get in there and fix it. Yeah, I think a lot of the other ones are like 10 or 12 bucks at this point. Anyway, okay, so I'm going to run that, and I'm just going to produce 30 frames worth of video to start with. And then let's look at it in Audacity, which unfortunately doesn't accept command line arguments, or I wouldn't have to do this every time. NTSC out. Yeah, Indianness doesn't matter when you're dealing with 8 bits. I don't care about the sample rate. So let's have a look at it. So any of you who know NTSC at all will immediately notice, oh, hey, it's upside down. Well, when I first started trying to do this, I didn't realize that apparently NTSC is transmitted inverted. So the level that they say is 0 in the spec is actually maximum amplitude. So I spent a good 10 minutes, 15 minutes messing around with this. Fortunately, I had already captured a version, a little chunk of the transmitted NTSC signal that they were using just to put stuff on the TV screen for people walking by. So I looked at that really quickly and was like, oh, it's upside down. And flipped it around, and guess what? It worked just fine. So yeah, there we've got the signal. And let me now transmit it. Don't look at the frequency I'm using, because, yeah. The great thing about transmitting black and white is I also don't need to use the full bandwidth of the NTSC signal. The chroma just kind of winds up getting clobbered, but I don't care about the chroma in this case. Oh, one thing I forgot to do is make a longer file. This is only going to loop every second, and so it's going to glitch just a little bit. So let me rerun this.
Hold up the webcam so everyone can see.
I've got a plan for that. Okay, so and that involves doing this,
Your own webcam.
so to speak. Did it pick it up, or did that screw it up? Okay, cool. Hi. Okay, so turn it on, and got nothing. It's probably because in the transport over here, I managed to foul it up. There we go. So hey, there we go. Let's test the range, pass it back. See how far 10 milliwatts gets me. So where is it now? Oh, we got to go faster, faster, faster. Yeah, that's next year. I'm thinking NyanCat, because NyanCat's got audio, right? Although I think they're pretty fierce about protecting copyright on that thing, weirdly. Still looking good? Right on. Okay, yeah, so we're all the way in the back of the room for those watching at home. Yeah, all the way at the back of the room, which is probably 40 feet, 40, 50 feet. And I just killed it, so I guess I can let it run. Anyone who's still got an analog TV and tuning around right now in the neighborhood's probably going to get a terrible surprise. So these are things that I typically do when I'm working with software-defined radio, and GNURadio isn't quite right for me. I hope that you got something out of this, that I'm a big Python fan, and maybe once I get some of these tools published, you'll find a use for them and can maybe help me enhance them, because there's definitely a lot of improvement in the way these commands work. Thank you very much.
Thank you. Very, very cool stuff. Any questions? Everyone's just been totally blown away by the Watchman, right?
Like less of a question, more of a comment. Like actually, Tim has written, like, or she has written PyQt graph, PyQt graph that's actually like you want in Spectrum to just display the waveform.
Yes.
It does that.
Cool. Can you give it command line arguments and have it pop up?
Well, ask Tim.
Okay. Well, and if not,
Yeah,
patch is
it's pretty
welcome,
easy
right?
to patch it.
Yeah. Yeah, as I was doing this, I was dreaming about having something that I could insert in line in the command line pipe string that would pop up like a live graph. And if I had several of them inserted, it would pop up several of them all in the same window that I could just look up and down. I didn't mention, but one really handy thing to do when you're debugging and building these chains is to just drop in a T, so you can send the stream of data at that point in the pipe stream out to a file. And then you can load it up in Spectrum or Audacity or whatever. So that's super handy. And then you can stack on additional stuff as you start learning more and more about the signal and the things you want to do to it later after that T, but you've still got those output files that you can look at to see all the intermediate stuff. So So it's not unlike using a file sync at several places throughout your flow graph. It's just a slightly different way of working versus GNURadio.
Any other questions?
Uh-oh.
I think you mentioned that the one tool, the packet stats utility, that's in your TPMS repo. Is that
Yep.
right? And you had
Terribly unmaintained.
you had a couple of clock recovery command line tools. Are those published somewhere?
They are not yet. I wrote them today. But I pulled them out of Portapat code. So success was more or less assured. I just had to wrap a command line interface around it. Anyone else?
How did you know the CRC was in bits and payloads?
Well, so that's what I was talking about with the bit stats, is it shows you a distribution of, so let's say I've got 1,000 packets that I run through this bit stats tool. I can see what the distribution is for each bit position in the packet, how many of those packets had a 0 there versus a 1. And by experience, especially dealing with TPMS packets, but it's applicable to a lot of simpler packet types. A lot of the different cheap transponder devices you see popping up here and there. Inevitably, the CRC is at the end, a CRC or checksum, and it always has a sort of a very even distribution of values. So you wind up with 8 bits or 16 bits that are all roughly 50% zeros and 50% ones. And so that's just a very strong hint that that's where you should be looking. It's not a guarantee, but if it only takes a few seconds to type out the command for brute force CRC to test a theory, then that's what I do. There are occasions where I found packets where the CRC was not calculated over the first several bits. And so I would incrementally move the front of the packet in until suddenly the CRC was able to be found. So it's very much just trial and error, and also just accumulating a certain amount of experience, knowing that this is how usually things are done. Note to anyone who wants to build a transponder device that is harder to hack, put the CRC at the front, and you'll mess me up really bad.
All right, one more round of applause. Thank you very much.
Thank you.
All right, so next up we're going to have Martin Brown. All you got to do is call it to me, right?
Is that yours? No, it's not. I left mine a mile or an hour away from here. Brought it all the way to Colorado and then forgot to bring it today.
Have you called me authority?
Oh, you're going to want the microphones.
Oh, yeah, that was microphones. How do I do this?
So the one with the red tape is the one that was acting up. So it may not even be. So I just tried
Okay, so these. How do I know if it's working or not? Hello. Oh, wait a minute. Hello. So this one should. Guten Tag. So this one's important? Okay. Now, phone you up, right? Why did all my windows go? I don't get it. Something's odd. What did I have? Hangouts. So I just do start a hangout and call you up instead. Cyberspectrum. Is that right? Okay, while we're setting this up, I've got a confession to make. Okay.
Are we?
Just share your screen and mute your microphone.
Oh yeah, share screen. This one, right? No. No, there it is. Top left. Desktop. Is that good? Awesome. Okay, so as I said, I have a little confession to make, and we've had 4 days of conference. It's 9, and I'm really tired. And so first thing is I'm following in the roots of Jared, and like him, I will be. Where is it? I'm going 1000% demo. Hell yeah! And yeah, no slides. I actually, you know.
You have to do more than the double thumbs up.
Oh, is this good? Yeah. But I've been talking about PyBOMBs all week, and I'm trying to sort of evangelize it. And I will do it one final time today, and then hopefully everyone's convinced. Yeah. So. And please make it interactive. Just shout out faster, slower, ask questions, because otherwise I'm just gonna, you know, forget that you're here and start reading emails or something like that. I don't. That would be really embarrassing. Okay, so I have 2 sort of sections, and really the idea is of this presentation to give anyone who has no idea about GNURadio like a good foundation to start on, and actually put them all the way to writing their first code. And if you like, and I'm not even kidding, you can just whip out your laptops and follow along what I'm doing here. Okay, so quickly, PyBOMBs again. So who does not know PyBOMBs? Ah, come on. Okay, I'm just gonna request that you ask me to speed up or slow down, as I said. So what is PyBOMBs? It is a tool to install all kinds of things out of tree modules, GNURadio, etc. So how do I get PyBOMBs? I do something like sudo pip install PyBOMBs. Hit enter. And I'm not actually going to fill out my password here because I want this to stay like that. But this is what I do to get PyBOMBs. This is all I need to do, and it's there. And I can also...
You make it bigger?
Oh, yeah, of course.
How did you get into pip?
How do I what?
How did you get into pip?
How did I get PyBOMBs into pip? It's very easy, but I don't want to go into that right now. So the pip is the command line that connects to the Python package index, and it's like where the deb files go for Debian, or like npm or gem or all of that. And it's really easy, but I don't want to go into that.
Submit to some central authority.
Yes, but they don't review it. So one thing I'm not going to talk about, but which we also have now, what's PyBOMBs GUI, is the GUI for PyBOMBs. Looks like this, and it's sort of hidden behind that other window. Why did it do that? Let's just open a new one here. PyBOMBs GUI. There we go. So it looks like this. It looks a lot like Synaptic. Choose my thingy. Yeah, there we go. And close that.
How did you bring that up? I'm trying to follow along.
So this is PyBOMBs GUI, right? So I launched a program called PyBOMBs GUI, and then I click this button, choose prefix, and that opened this. I'm going to talk about what a prefix is in a sec. I'm selecting my default here, then I need to close this window, which won't let me do right now. Oh no, there we go. And this is a list of packages that I've currently installed. And you can see it has all kinds of out of tree modules here. So gr, cdma, and deck2, and whatever all they all are. So AirSpy is, for example, is installed because it comes with the default installation. But all of this will make more sense, I think, after I explain what all these words such as prefix, etc. actually mean. Okay, close that again. Go back to my command line. I have the GUI open multiple times. Close it here. Okay, boom. Start from scratch. Now, we have PyBOMBs installed. What do I need to do to install GNURadio? So something I need to highlight is that PyBOMBs actually has a manual, and it is on the PyBOMBs GitHub. So it's down here. You can just follow all of these instructions. It's not a lot, and it says, this is if you want to install it from source, or this is if you want to use pip, which is the easiest way. Here's the quick start guide. I recommend just going through that and then running all these commands. And these two commands in particular will install a bunch of recipes on your computer, which are what you need to actually install anything. So imagine PyBOMBs is like apt-get, so it's the executable, and then the recipes are like, well, you know, they're separate lists that control what you can install. So they don't ship with PyBOMBs, and that is for a very good reason. So these recipes make a lot of sense for most people. But if you say you're in your company network behind a firewall or something, they wouldn't work. So you'd run your own recipes. That's how that works. And then, for example, Edis has a bunch of recipes that are outside of those because there's so many of them and they get updated quickly. And this is sort of a central repository. And we have two central repositories, one called GRecipes, which is sort of the baseline repository. And then GR etc. is where we put everything. Anything that goes, you know, software radio, whatever. So, actually, we might put that into recipes. Okay, so why PyBOMBs at all? What's the point? So one of the many reasons is I can install stuff very easily into my home directory. So I have this directory called prefix here, which is where I have different installations. So in each of these directories is a different installation of GNURadio that serves a different purpose. And I can very, very easily switch between them. I can delete a complete installation of GNURadio and all its dependencies just by removing that directory. And I don't need sysadmin rights. If I run PyBOMBs prefix info, I will get the similar list. You'll see that these directories are assigned an alias, which is the first line. And I can use this alias to identify which one I want to use. So if I do PyBOMBs-p rfnocdevil, for example, PyBOMBs will know, okay, from now on, everything that I'm supposed to do, I'm going to do in this prefix instead of the default one. And I know this is the default one, not because of the name, that's just a convenient one, but because I actually selected it as the default. So let's say I want to install GNU, let's say I'm still starting from scratch. Let's say I don't have any of these prefixes. So what I can do is something like this. I do PyBOMBs prefix init -r GNURadio default. So -r is a recipe for an entire prefix. And -a is an alias. I'll choose default 3 because I'm running out of names here. And then I just go to a path like prefix, foobar, or I could call it default 3 to keep the name consistent, and hit enter. And it'll try and figure out what the dependency tree is. And you'll see this is the dependency tree because this recipe installs grosmo-str, which pulls in all kinds of dependencies. And then it fails because it can't install RTL-str. I had that same problem at the conference, and I thought it was actually the osmo-str server, but it's the fact that the university Wi-Fi doesn't let you do git clones through the git protocol. So this is actually great for this presentation, though, because then I can show you how to go into a recipe. So I can do PyBOMBs recipes, recipes list repos, and this will show me all the repositories for recipes. It's wrapping a bit. I usually have more characters. And I happen to know that this recipe that I just used is in here, so I can just actually open it, GNURadio-default. This is what the file looks like. Very simple. So it says, okay, if you initiate a prefix using this recipe, these are the packages that you want to install. And then, or actually before that, you will set a couple of configuration parameters. I don't want to go into these right now. That's more advanced. Actually, I don't want to talk about these at all today. But to fix this immediate problem, I could say, well, I don't really need grosmo-str right now. I'm just going to delete it from here, save that file, and then run my original command again. Oh, wait a minute. This is, okay, it started creating the prefix, and now it has a file. I'm just going to call it default 4 then. There we go. And now it doesn't need RTL-str, and you can just start cloning UHD. Okay, and this will take forever. I'm not going to complete this. Pretend like I ran it, and now I have PyBOMBs prefix info. Now I have this wonderful default prefix available. Now, you know that if you install stuff by source, compile stuff by source, and put it into user local, it'll just be available in your path. If you put it in some random directory, it will not. So how do I fix that? There's two ways to do that. So first of all, I can do sort of the Docker style, where I do PyBOMBs run GNURadio companion. I'm just going to pick GNURadio companion. And actually, no, I can do something even fancier. I can do which GNURadio companion. And what it'll do is it'll run this command in a session that has the right environment variable set. So let's do that. And you can see it returns, oh, this is the executable that I would run. Whereas if I do PyBOMBs-p rfnocdevil, then it's a different one, okay? And I can also permanently activate a prefix in this shell by doing source. Source is a command that changes your environment. Oh, that's one thing it can do. Default and then set up env. And if I show you my environment now, you'll see, for example, this environment variable PyBOMBs prefix is now new, but also my path. My path now includes the prefix at the beginning. So this is how I can navigate in PyBOMBs prefixes. Now let's say I want to add something to this prefix like grpaint. I just do PyBOMBs install grpaint. And oh, actually I did that today at the conference, so it's already installed. I don't know, PSK31 is another small one. I don't want to do a big one. So it'll clone it, it'll configure it, it'll build it and install it, and I can even remove it again the same way, and then it'll try its best to cleanly pull it out again. And so I can very, very easily, without having to go into a lot of hassle, modify the contents of these prefixes. Now, in these examples, all it did was clone source code, build it locally, and then install it. PyBOMBs is actually, so that reminds you a lot of the Docker concept. It's actually a bit different because PyBOMBs can also install things into your system if it thinks that's the right thing to do. So if I do PyBOMBs install in Spectrum, for example, it'll generate the install tree, and it'll tell me that I need Qt5. I don't have Qt5, which is a dependency in Spectrum. But PyBOMBs has internal rules that say, okay, but I actually want to use apt-get install to use PyBOMBs, to use Qt5. So if I enter my password here, 123 QWE, whoops. It'll actually run apt-get install in the background and then do stuff. And then it'll actually fall, once it's finished that, oh, this is going to be probably. So I have a rule like how many weeks before GRCon I don't update anything. And okay, whatever. So you can imagine what's going to happen. It's going to install Qt5 dependencies. And once it's finished, it's actually then going to clone in Spectrum and then build it from source. So it can do both. So let me look at my notes. Yes, there's one thing I want to highlight. Oh, there we go. So I'm not quite sure why this. I've never actually tried installing GI in Spectrum through PyBOMBs. Oh, Liquid is. Oh, okay. So then the recipe is broken. That's fantastic because that means I can. Ah, so Chris is the guy who keeps up to date with all the. Is it in recipes or is it in etc.?
Probably in etc.
Okay, so I'm just going to pull that up real quick. And this is the recipe for in Spectrum. You can see it has two dependencies, GNURadio and Qt. Does it actually depend on GNURadio? So okay, well I could just say, okay, I'm just going to change that, and then what's the other one? Liquid, something like that. I don't know. Okay, I'd have to look up the name of the actual. Whatever. I'm not going to. Can you do that, Chris, please? Can you? Yep, thanks. Okay, one final note about PyBOMBs. So for those who do embedded work, especially if you do one specific use case which I fixed with PyBOMBs was people setting up rfnoc development for the E310. There's a lot of things you need to install and get right, and PyBOMBs will just do that. And as a matter of fact, PyBOMBs prefix info, this environment here is specific for cross compilation. Now, if I do something like this, PyBOMBs-p E300, so I select the other prefix, which is not my default, prefix env will show you the environment in which any command runs that I do in here. And you will see like stuff like this here, where we have, obviously we're using cross-compile linkers, assemblers, and compilers. So this is clearly not the environment that I'm currently running in. So this is an easy way to just configure all those things. But if I want to install an out-of-tree module, for example, I just do PyBOMBs-P E300 install grpaint, and I think that's also already installed, yeah. But the point is, if you do this by hand, then you have to change a lot of CMake variables. Now you don't. Okay, that's PyBOMBs. PyBOMBs in a nutshell. Any questions on PyBOMBs?
That environment set up for the E300, that have been programmed in after you made the initial prefix, or do you give it like a tool chain and figures it out, or how is that initialized?
It's a big question. So let's just go into the prefix and take a look. So actually, when I install it, it actually does something a bit different than the other. First it'll download the SDK. Then it'll install the SDK into that prefix. And then it'll, and this is something that is controlled through the E300 SDK recipe. That's how PyBOMBs knows how to do that. It'll source this file before running any of the other commands. But you can actually change any environment variable within PyBOMBs. By the way, something I sort of gloss over, the difference between a PyBOMBs prefix and any other directory is actually, there is actually no difference, except for most of the times we have this hidden.pybombs directory in there. So if we go there and take a look, we will see, for example, this config YAML file. And this is what sets up my prefix. And for the E300 SDK one, you can see there's all kinds of settings that we override. And for example, if we do an install, we don't do the regular install, but we use the destr thing. And I'm pretty sure, yeah, there we go. So to set up my environment, I run this command. So that's how PyBOMBs does all of that. One thing that's nice is you can see everything gets installed into user, and then we have this so we have this setenv shell script. Does anyone know what this does? What the point of that is? What?
Well, it removes every kind of pre-configured, like it sets the paths that your runtime loader.
Okay, so so I can use this for active development. What I'll do is I connect my E300. On my E300, I SSHFS this user directory. So let's pretend I'm on my E300 and I mount this to ls, and this is what I see. And I have to just, if I just source that, then I have the PyBOMBs recipe active on my E300. And that's useful. Like no hassle with any other kind of command line thingy. Okay, I really don't want to talk about PyBOMBs anymore unless there's questions. I'll happily answer any questions, but that's all I have to show. I have a second section I want to move on to. But I will answer your question. If you have. Looks like I've exhausted PyBOMBs. That's good. Finally. So what now? So you were a newbie until 10 minutes ago, but now you know how to install GNURadio and all the out-of-tree modules. Fantastic. And you've played around with GNURadio at this point. You want to start writing your own code. Okay, so let's do that. And there's a tool called grmodule. And let's go into my default prefix and add an out-of-tree module that we then compile by hand. Okay, and I'm going to call it grmodule to create a new mod for a new module, and I'm going to call it cyber. Boom. So we create this directory grcyber, so let's go in there. It's currently empty. And what I'm doing right now is all explained on this tutorial, guided GNURadio tutorials. So you can if I'm going too fast, you can follow this very easily later on. So this is sort of all the boilerplate. And this is actually quite interesting to see. We have 1.2 megabytes of boilerplate. Boom! Imagine you had to handle any of that by hand. It would be crazy. Actually, I'm surprised it's so much. Okay, it's Doxygen is doing most of that. But still, and that has 0 blocks in there. But let's add one. grmodule add -t sync for a sync block, -l cpp. You want to do this in C++. We're going to call it squareff. So this is a convention in C++. Sorry, in GNURadio, by the way. Square is just the block I'm going to write will square your input. And then _ff means it has a floating point input and a floating point output. Let's do that. It'll ask you for a couple of questions. It'll ask you a couple of questions. Do we want any arguments? No, we don't. Do we want Python QA code? Oh yeah, that sounds great. Do we want C++ QA code? No, we don't, because we already have the Python, and it creates all those, all the boilerplate. So let's open some of those and start coding. So, where is it? Editor. Oh no, not again. There we go. So these are all the files that get generated. So because we are excellent and very disciplined coders, we'll start with the unit test, of course. So the files that get generated have these tags here, these square bracket plus thingies, and I chose those because in most Vim settings you can just jump to those. So I can just select that by hitting a button. So copyright, me, and then that's it. There's no more boilerplate. So I actually, and now I'm going to speed things a little bit up. Okay, what I'm going to do now is I'm going to write a unit test for a block that takes a floating point input and then will output that value but squared. So I'm going to, where am I? PW, fallback, Python QA square. There we go. I'm just going to copy these lines over so I don't have to type them out again. And there we go. So what are we doing here? First, we are creating a source, which is a blocks.vector source. So it's a GNURadio block that can produce data. And this is my input data. So my input data is 0, 1, 2, 3. And my expected data, I can pre-calculate that in Python, is simply the square of the input data. So that's that. Then I'm going to create an instance of the block that I am yet going to write. Finally, a sink, which is where the data goes. I connect those, source square sink, in a line. And this is the same as when you're when you're in GNURadio Companion, drop down those 3 blocks and then draw the arrows. Run that, and then assert that the output data is the same as the expected data. Okay, so I have to create a build directory. I'm going to do that, and then I'm going to run CMake. Now, PyBOMBs will only get you so far. If you create with gmodule, create an out of tree module in a prefix, you will have to say that use this prefix. But you can use this PyBOMBs prefix environment variable. So let's do that. And there's some warnings. We can ignore those. I'm just going to run make. And it'll fail. Why will it fail? Because I haven't written any code yet. So that's test-driven development. You want to see stuff fail all the time. So that's actually literally what you're supposed to do. So there are 3 C++ files that you need to edit. I'm going to go through them in order. The first is the public header. And the public header is something you would change if the block had some argument that you would need to change at runtime. So for example, if this wasn't just square, but was arbitrary power of n, then I might have something like void set powers or something like that, right? But I don't, so I'm just going to leave this out. And so I don't actually have to change this file. That's great. I'm just going to close it so I have less clutter. What the hell? Did I just close it? Look, it doesn't matter. I'm just going to start it again. Okay, I was going to close this. Then I have another header, which is the internal header. I also don't need to change that. That's something that's also explained in the tutorials. I'm going to close that. But this is the interesting one, my actual block. Now, you can see the block has 70 lines of code, and there's zero stuff in there. So it's good that gmodule creates all of that. And we don't even have to read it all. We just have to follow the jump marker. So I'm just going to hit Control-J, copyright me. I don't really have to change that. And then first we have to define what's called the I/O signature, which is how we declare to GNURadio how many input and output ports we have. So we have 1 input port, and so it's exactly 1. So it's minimum and maximum is both 1. Type, float, same on the outputs, 1, float. And now I jump into my work function. My pointers should all be of type float. That'll make my life really easy. And then I'm already here. Do signal processing. And so I can put in a little for loop here. Whoops, no, there we go. I'm going to iterate over all the items that go into this work function, and then I will simply say out I equals in I multiplied with in I. Okay. Seems fine. Let's try it. I'm just going to go back to build, run make, and it works. Maybe. Swig always takes a while. Now, before I do anything else, I run my unit test now, make test, and it works. Nice. Okay, so now I know that my block works, but really I want to have this block in GNURadio Companion. So there is a nice little, yes?
Could you show real quick, where do you put comments to get them properly pulled into the GRC block? Because that never works for me.
What? What do you mean by comments?
I want to put documentation in the files themselves, the source files, but have them pulled into the...
Yeah, so you put them into this file, the doc block, but I heard there was some bug recently but that was fixed, I think. But stuff you put in here would get pulled into GRC. Hope, or at least it should. Actually, we'll see if it does.
What stage actually parses that? Is it Doxygen?
Yeah, so it's Doxygen into XML, and then we have Python that pulls the XML stuff out, and I think Ben wrote that. Is he here? So you can complain to him then. I'm going to...
But if you choose not to compile with the Doxygen, then you will lose all docs for everything, right?
Yeah. Okay. I want to get some traction here. So this is sort of an example XML that gets generated, and this is what we need to pull it into GNURadio Companion. Now, for very simple blocks like this one, we actually can use gmodule, make XML square, and it'll look for stuff that matches that regex, and it says, oh, there's squaref. Do you want to override the existing file? I'm going to say yes, and if we go back to my editor, it'll actually have the correct XML in it, so I don't even have to write any XML. So if I go back to my build directory and do make install, let me just check I'm running the right prefix. Yes, that looks good. I'm just going to do GNURadio Companion. I'm just going to launch it here. And I should have cyber. There we go. There's our cyber module. So I can go ahead and drop that down. I'm going to add a throttle and a signal source and a Qt GUI times sync. Oh, no, that's the wrong one. Click. There we go. So time sync, square, signal source goes here. Throttle. Now this, and this guy needs to be changed to float. We add some arrows. Sorry, what?
Nice skin.
Yeah, I use moisturizer. And press my new favorite button. Save this file, and boom, I can. Oh no, wait a minute. I wanted some even fancier tests. So this is my squaring, basically in graphical form. So I'm going to compare the squared input with the unsquared input. So I'm just going to select this, and you can see I have a sine wave and a squared sine wave. So this block is working wonderfully. So that's how easy it is to add blocks to GNURadio. So how much time? What's the?
You're good.
Okay. So for my final trick, I would like to take some requests for a block that I'll write in Python live, and I'm only going to accept very simple suggestions though. Something that is a sync block. Clipping. Okay, so what are we looking for? So give me some precision. Give me some. What precisely explain what the block is supposed to do? For every sample that comes in,
You put in complex numbers and restricts to like the unity circle. So if it's large, like if magnitude is larger, it just ends up on the unity circle. Below, it's just the original. Can we have that unity circle be a variable?
Okay. Okay, I'm gonna negotiate this. I'm gonna negotiate this down. I'm gonna make the unit circle a variable, but then I'm gonna restrict it to real numbers. Is that fine? Does that work? Okay. No, it's my it's. Yeah, I could, but then yeah, I could do that actually. You want me to do an embedded Python blog, or do you want to do an actual Python blog? Okay. So I hadn't prepared that. Oh, at this point, I'm completely. Okay. So I'm just going to use the signal source as my test vector generator, but I'm going to change the amplitude to 2, and then I will Python block going to connect this up. Clearly, I need to reduce the number. Actually, no. Let's do the same thing. I'm just going to compare that. I just made a mistake here. Has anyone spotted it already? Yes, I missed the throttle. Throttle, there we go. Doesn't matter where we put it, really. I'm just going to put it here. Does anyone know why that arrowhead is red? On the exactly. You are paying attention. Okay, so I click Open Editor. I'm just going to full screen that. So, let me see. Okay. So no. I'm just going to stick to my original. So I need to define in and output types, float. My example parameter is the radius, although it's a one-dimensional radius, so not really. But, okay. Then I'm just going to call this guy radius equals radius. And now into my work function. Now the difference between Python and C++ is it's nearly the same, but not quite. So first of all, you see the signature looks a little bit different, but that's fine because I can infer the length of the input and output items by inspection. But one thing to keep in mind, and that's very important. Even if you're used to Python, these are NumPy arrays, and writing to them is not quite the same as writing to any other list. So you'd think that this line is the same as this line, but it's not. Because if I do this, then I will actually create a new object, and then I will write to different memory, and when I return the work function, like nothing happens. So if you don't know this notation, then you'll have to look it up, because I'm not going to go into it right now. But this seems pretty simple. Now the reason to do Python is because it's very easy to prototype your algorithms. Some say this is slow, and that's definitely true compared to C++. But if you use NumPy tricks, then you will get very, very fast code in here. I'm just not going to do that right now, so because I'll have to look up NumPy, and I'm going to keep it slow but simple and easy to read. I'm just going to do something like this. First of all, I'm going to bind my input items to an easier variable, and then I'm just going to do very, very easy for loops. I'm going to index in. I'm just going to loop over the length of my input items, and I'm just going to do super duper simple. This is clearly not optimal. This is not how I write code professionally. But hey, it's 9:30, guys. Give me a break. So I'm just going to do if in 0 index greater than self.radius. Radio, yeah. Then I'm going to do out. And this guy. Actually, I'm going to bind this as well. Output items 0. Out index equals self.radius. Oh, I did it again. And if it's less than that, then I'm going to do this. And actually, I need to do one of those. And then else, I'm going to do this. Out equals in.
If it's less than minus self-radius? Less than minus.
Yes, exactly. Thank you very much. And this should work, I believe. Yes, thank you very much. I can run this through syntactic, through Pylon if I like. It'll flag some things which are not, which it can't. Something I like to do with Python, I just run a static syntax check before I save. Okay, boom. It's already picked it up. I have radius now.
Do you know what actually at the back end goes through and parses the code?
Something that Sebastian wrote.
Or is it Python introspection? Cool.
Change this, and I don't know. Ooh, guys. Okay. I hope I've convinced everyone that it's very, very easy to add blocks. So embedded Python. If I'd have done the regular Python, I'm not going to do it now. Obviously, this would eat up too much time. But if I'm just going to show you the command line that I would have used. Actually, I have so this is not the first time I've done that, and this is the first time I've actually got a good suggestion. I have a fallback suggestion in case the audience doesn't provide me one, and it's the what is it? It's a fizzbuzz in Python and this is the command line. So a fizzbuzz in Python in GNURadio. So gmodule add to create a block -t sync because it's a sync block -l Python, which is the programming language, and then the name of the block, and it'll create all the files. And the one advantage over the one advantage that the regular Python blocks have over the GRC ones, well, there's two actually. First of all, you can use the regular Python blocks without GRC, obviously, but then also you can write unit tests. So I don't know if you can do that. Can you do that with embedded Python blocks?
When you generate, it draws the file next to the program itself.
Oh, okay. So if I hit F5, then where am I? CD build, and then it creates. Where is it? This one here?
Yeah.
Oh, okay. Oh, there we go. Nice. So cool. I didn't know that. I learned something even when I'm at the podium. Okay, that's GRModule and PyBOMBs. That's all I had for today. Is there any? I can answer any more questions if you have it.
Any questions from anyone? Yeah, question?
You
Speak right into it.
Yeah, to activate PyBOMB env, you called that script, right? Setup
Yeah.
env. Do you have like a PyBOMB subcommand to do that? So I can like sort it by name and not have to know the path? Like the alias?
I wasn't paying attention because I just wanted to.
Never mind.
No. Do I have a PyBOMB subcommand? Usually the answer is go PyBOMBs help, and then I get all of my subcommands.
Okay, which one calls the setup env?
Calls the so they all do, and then but once they exit, you will get your regular environment back, right? So
If I source that, no.
Well, if you source it, then you have it in your current shell,
Yeah.
obviously. But PyBOMBs will actually, so when PyBOMBs runs external commands, whenever it's appropriate, it'll apply the environment that you configure for PyBOMBs. So if I do PyBOMBs run foo, then foo will be run inside that PyBOMBs environment. But for example, apt-get install will not, because it doesn't need to. Does that answer your question?
No, but it's okay. Can I change the default?
The default what?
Like you set PyBOMBs run.
Oh, you mean the default prefix? Yeah, sure. So PyBOMBs config will let you do all of that. So I can do PyBOMBs config without any arguments. It'll show me all the standard variables that I have, and one of them is default prefix. So I can do PyBOMBs config default prefix rfnoc devil, for example. And then if I do PyBOMBs run which UHD user probe, it'll return what? Okay, I should have returned the one from rfnoc devil. No, the whole point is that I've changed the default, so I don't have to. Wait a minute, did that actually trigger? Wait a minute, PyBOMBs prefix info. The default is rfnoc. I don't know why that didn't work, but that's how it's supposed to work.
Okay.
Oh yeah, you're right. Because currently, yeah. Right, so here it'll work. So PyBombs, I hope, run which UHD user probe. Yeah, and if I do PyBombs config default prefix default, so set it back, then yeah. Okay, thanks. No more questions? Okay, well then thank you very much, and
Thanks, Martin.
off to the next video.
Sylvain, you want to do it? You ready? Yeah, sure. Okay, just while Sylvain's coming down to set up, there's one video that we're going to play. Neil, do you want to explain this? You're probably better suited to explain this. You can get up on this too, if you like.
So I think it's working. So the folks at NewTAC up in Montreal in Canada have asked us to make an announcement. So they're going to announce their LTE workshop series, which is a series of LTE workshops that basically focus on the implementation of LTE on their hardware platform. And they've asked us to do a public announcement for this workshop series. It's free. It's open to the general public. And there's something like 7 sessions that are going to be run over the next 2 months across the U.S. So we're going to play their announcement here now. I'm the director of business and product development at NewTAC. I would like to invite you to a free full-day workshop that will present in 8 different cities in the U.S. in the upcoming weeks. For those of you who don't know NewTAC, NewTAC is a leading provider of advanced digital signal processing solutions and wireless technologies, including SDR, software defined radio. The workshop is technical, it's not a sales pitch, and it will discuss advanced scenarios of LTE on the SDR. These are the topics we will address in the workshop. We will learn the SDR platform architecture and the flexibility it offers, how to configure the inode and the EPC to build a private LTE network in one box. We will learn how to set up a remote EPC and use carrier Ethernet to back up LTE. We'll explore the handover mechanism between inode Bs. We will test LTE multiple cells concepts, such as interference between multiple UEs and multiple cells. We will learn how can an SDR-based UE help us implement a network using non-standard frequency bands. We will explore carrier aggregation, intraband contiguous, intraband non-contiguous, and interband. We will explore the MOCN scenario, where multiple EPCs are running simultaneously, interfacing with a single node. We will learn how SDR can be used in the context of tactical LTE. We will look at all these use cases from both an industry sector and a defense sector angle. The workshop will be presented by Muhammad Akhtar, a PhD and field application engineer at NewTAC who has extensive experience on SDR platforms. Has worked with tools such as GNURadio, MATLAB, Simulink, and Xilinx system generator on software-defined radio platforms. He developed a high level of expertise with the Amerisoft LTE stack and is also a Cisco CCNA and CCENT certified engineer. As mentioned previously, we will be visiting 8 cities in 6 different states. The workshop lasts a full day from 9 to 5. It's open to everybody and it's free. For more information on the workshop or to register, please go to newtac.com/LTE
LTE-workshop-USA. The seats are limited. I hope to meet you all there. Bye-bye.
Output.
And then you're going to call me.
Yeah, yeah, I can do that now. Video call. Berlin 256.
Yep. There we go, got it. All right. Yeah, so just mute your stuff. I can see your screen. Yep, all set. All right, let's give somebody
No data, same. I just need to figure out, how X-render works. Same as EDP1. Is that, of course not, X.
You're the master, aren't you? What? Oh, sorry. Yeah.
Okay, so that is good. So yeah, I'm talking about GMR1 sat phones. I'll start by a quick introduction onto what is GMR1. Then I'm actually going to show how to use Osmo GMR. Obviously, I'm going to work from captures because we're inside. So what is GMR? GMR stands for Geomobile Radio, and it's basically the outside of me? It's outside of me, I can assure you.
On your other side. Yeah.
Is that okay?
That's nothing.
Okay. So it's an ETSI standard for satellite phones. It's heavily based on GSM, which is good for me because I started looking into telecom standard with GSM. There's actually two standards called GMR1 and GMR2. They are not evolution of one another. They're like competing standards that have been developed by different companies, essentially. So far, we've only worked on GMR1. GMR1 has gone through kind of 3 evolutionary steps. GMR1, base. Then GMPRS is when they added packet data, which is like GPRS for phones. And
There is 3G, where they basically mostly improved packet data, internet access, and they also evolved the core network to move to the 3G core network, basically. So where is it used? One of the main providers is Teraya. That's the one we've looked at the most, mostly because it's visible from Europe, which means I can actually see it and receive signals. And secondly, it's because it's pretty much the only one we could find. The good thing is that the Mexican government has recently launched Morelos 3, which is a new satellite which is designed to provide GMR1 3G coverage over Mexico. And it's visible from the US. I mean, several people have already received it. At the moment, they're in the commissioning phase, which means the signals are active, but we don't see much traffic yet. Actually, so far we've actually seen some channel being assigned, but it's really like from today, so it's really recent stuff. There's supposed to be 2 satellites. The first one blew up, so yeah, there's only going to be one.
What do you mean blew up?
I mean, it's the launch. Yeah, during launch, it was a Proton M that blew up a year ago, something like that. Yeah, that happens. There's supposed to be other providers, right? If we look, the companies I've listed here, EchoStar Mobile, Skytra, TerreStar, ICO, they all have spectrum allocation. There is even satellites up there that have GMR payloads, and they talk about it in press releases and stuff like that. But you can't really find much information, especially since for at least a couple of them, like the first company that started went bankrupt, and then the satellite has been bought by some other company and transferred, and it's kind of hard to find up-to-date information. But I mean, on eBay you can find, for instance, you can find Skytra phones. So yeah, we're looking. If you want to look and you find them, that'd be great, because we're looking for more signals. I'm not going to talk about the GMR2. So a quick comparison to GSM. The first thing they did is they renamed everything by adding geo in the name. So like, it's not a base transceiver station, it's a geo transceiver station. It's not a MS, which is a mobile station. It's a MAS, which stands for Mobile Earth Station. It makes life complicated, but when you learn to just add G in front of everything, it's easy. They added some specialized feature that are really required when you're working, with long delays and stuff like that. Terminal-to-terminal calls. That's basically where a terminal can directly talk to another through the satellite, but without going through the core network, basically, and that would use the delay in half, which is good, because it's a geostationary satellite, which means it's pretty far away. They also added something called high penetration alerting. And that's because you really don't receive the signal when you're inside. But I mean, if you're inside, you still want to know that somebody is trying to call you, and so they have like this specialized channel which has an insane amount of error correction, so that even when you're inside with a really crappy signal, your phone can tell you, okay, somebody's trying to call you. You should run outside within like 20 seconds to take the call.
Insane amount of error coding. What are we talking?
I mean, like, it takes them 10 seconds to transmit like the EMZ of the guy trying to call or something. It's really really redundant. There's a very tight link to GPS for 2 things. First is for billing, because depending on in which country you currently are, they're going to bill you different tariff, or even possibly refuse service altogether. And this again is, I mean, they need to pre-adapt timings and stuff like that, so it does have some usefulness. You can see that integration, for example, because to help the phone acquire a GPS lock more quickly, they actually send the GPS almanac and GPS ephemeris on specialized channels, so that you can acquire, from scratch, get a lock much faster, even if it's not a GPS, like you don't have any assistance data. And something that's nice as well is that every time you establish a channel in the array.ch packet, so the phone will send a packet, and that packet will contain your current GPS position. And obviously at that time,
encryption is enabled, so every time you place a phone call, everybody can see where you are, basically. They also obviously went to a new speech codec because, whatever. And they invented a new cipher, and I put new into quote marks because what they did is they took A52 and they basically changed the position of every taps in the linear feedback registers, but it's the exact same structure as A52. So there's nothing really new. If we look a little bit at the protocol stack, basically anything that touches the phi, like layer 0, layer 1, is completely different, adapted for satellite types of channel and try to save power and that kind of things. On the layer above that, layer 2, which is the link layer, it had to have some minor adaptation to deal with the fact that you have a huge latency, like hundreds of milliseconds between when you send a packet and when the core network actually receives it. So the size of the window is longer. On the layer 3, things start looking really much the same. RR, which is a radio resource, it's basically, when the core network assigns you a channel, it's going to describe that channel, like which frequency and stuff like that. Obviously, that's different because the channels are different, but everything above that, above radio resource, is basically the same. And it actually uses a GSM core network, and it uses GSM SIM. Like I take my SIM card, put it in a Turaya phone, and I can roam onto Turaya. Right? Which is really useful for testing if you don't want. However, be aware that it's extremely expensive. Yeah. Well, I mean, I think I placed like a 3-minute phone call, and I had 60 euro on my. Yeah, it's insanely expensive. I mean, you're basically roaming onto a satellite. It's cheaper to buy a SIM and use that. But unfortunately, there is no free phone call. Like even calling your voicemail is you pay for that. So it's not easy to generate data freely. So I mean, GMR1. I'm mostly going to focus from here on the the RF side of things because it's Cyberspectrum after all. So the physical layer, the spec described first it's spot beam coverage, right? Everybody knows what spot beam is. Yeah. Okay. Okay. So what they do is that on the satellite they have like a giant reflector, like 20 or so, with 128 elements, and they do digital beamforming so that the pattern on the ground appears like a different beam for different areas, so that they get better signal and they get basically kind of like cell coverage, like like a cell network, except the cells are pretty huge. I mean, like there's one cell pretty much cover like Belgium or something. So it's not really small cells, but it's still cell nonetheless. What that mostly means is that if you're not inside that particular beam and you're trying to see other beams, they might be weaker or they might be mixed together, right? Because you don't have the correct phasing and stuff like that. So for example, if you're trying to look at BEXSAT from the US, some of the beam can appear clear, but most of them, since you're not in the target coverage area, most of them will be actually mixed together and not necessarily decodable, basically. Yeah, I mean, you can see them, but you can see that several overlap. I'll show a capture of BEXSAT. So the spec says that you can have coverage in L-band or S-band. Currently, we don't have any provider in S-band. Both MEXSAT and Turaya are in L-band. Both are using LHCP, and they use the concept of RFkin like on GSM, where the entire band is basically divided into this number channel from number 1 to 1087, and the relatively narrow band channel, like 30 kilohertz or so. The spec actually does describe the feeder link it describes the feeder link to the extent that it has feeder links, and they're in C-band or KU band. I'll talk very briefly about those, but I will mostly focus on L-band because it's much easier to receive because, I mean, you're meant to receive the L-band signal with a phone, so, they're strong and stuff like that. The C-band signal, you need large dishes and preferably tracking, and it's much harder to receive. So it's a TDMA pattern like GSM, which means basically at which time you receive a burst actually carry information that you need to decode that burst, because if you receive a burst at that precise time, that's actually going to tell you what type of burst it is. So timing is really important. The synchronization pattern they use is particularly interesting because it's a dual chirp that kind of looks like a X in the, if you look at it in Spectrum. That makes it really easy to know if you're tuned to a GMR carrier, basically, because if you see X, that's you're pretty much sure that it's going to be GMR. There's actually two variants of this synchronization pattern. There is the FCCH that lasts for 3 time slots, and then FCCH3 that lasts for 9 time slots. But except for the duration, they're the same waveform. Modulation-wise, it's mostly Pi4 CQPSK. So you have 8 constellation points, but only 4 possible transitions. So what you do to demode that is basically do the counter rotation and then demode it as a QPSK, basically. There's other variation of this that are used for different types of channels and stuff like that. Again, for data, internet access, they obviously needed more bandwidth, so they went to more complicated constellation, up to 32 APSK, which is really annoying to demodulate. There is also new symbol rates, like again, to speed up internet access. What they do is they actually aggregate several 30 kilohertz channel, and instead of having one channel, you have 5 of them that are grouped into one that has 5 times the symbol rate, for instance, and then of course then 5 times the bandwidth as well. So that's kind of what it looks like in a spectrum. That's a capture of MECSAT. And as you can see, you have all those X. In theory, there should be one every like 320 milliseconds, I think, and all at the same intensity, of course, and stuff like that. But since you're not in the target coverage area, you have actually several spot beams because they do frequency reuse between spot beams that are overlapping and kind of jam each other. Thankfully, if you have one that dominates, it will actually be decodable because the other are just considered as noise and diminish your SNR, but it's still decodable. The other nice thing is that to save power, the satellite doesn't transmit a constant carrier. If it doesn't have anything to say, it won't say anything, and there won't be anything. So that means that even if they're overlapping, sometimes you can actually decode both of them fully, just because they don't actually mix with each other too much. So if you want to receive it, how would you do it? The first thing you need is an antenna, obviously. You have a lot of options. Basically, anything that can receive L-band and is LHCP is going to work. You can even do it with linear polarization. We worked with offset dish. We've worked with helical antenna, which are pretty easy to build. We did biquad. We did some patch. You can even use a GPS antenna. It's LHCP, but if instead of pointing it at the sky, you point it at a giant metal sheet, it will actually invert the polarization, and then you get a LHCP antenna, basically. That works.
Can you do that with a building?
Yeah, that also works with buildings. Not as well as the metal sheet, but it works. I mean, basically anything that's going to reflect the signal is going to work. I'm sure the ground would work. Filters on LNA. They're optional. I mean, it kind of depends where you are. If you're in a kind of RF quiet zone, you might not need them at all. If you're right next to a GSM 1800 base station, that might be useful. Basically, yeah, I mean, you know what LNAs are and what they're used for. For the filters, we've used SAW filter we've extracted from phones. We also made, we add a custom cavity filter manufactured, which is really nice and really helps. Basically, you can plug it to your antenna directly, provide lots of amplification, not be annoyed by any interfering signals. You need an SDR. Anything that's supported by GR or Osmo SDR is just going to work out of the box. The requirements are not very high. I mean, when we started this project is not very recent. We started on it a long time ago, and just been working on it in the background basically. When we started, there was actually no RTL SDR. So the first reception was made with like USP or even FunCube dongles, which only have like 96 kilohertz of bandwidth, but the channels are so narrow that you can receive them. However, the more bandwidth you have, the better, because while you can receive several spot beams at the same time, it goes faster for scanning. And if you actually want to receive traffic data, most of the time the traffic channel won't be assigned on the same frequency. So like you're listening to the broadcast channel on one frequency, and then you'll get an assignment message, and that assignment message will tell you to go to another frequency. And if you're lucky, it's going to be right next to it. Like, for instance, like in Belgium, the broadcast channel is on 267, and the traffic ends up on 268. But sometimes they can be at the opposite end of the spectrum, and then you need an SDR that can pretty much listen to the entire band at once. Yeah, you need to be able to tune to L-band, obviously. I don't have any R820T dongles or any radio using those tuners, but I hear that sometimes in L-band they're not ideal. But if you have an LNA in front, it should probably work fine. And I mean, if you don't have GNURadio support, you can even go back to using FIFOs and source and do things yourself if you really want to. So how does the software stack kind of work? So obviously you have the SDR, and that goes through a first utility that is called GMR1RX L-band. And that's a GNURadio flow graph that's basically going to acquire the sample and do all the channelization work. This is going to write out the data to a bunch of either FIFO or files, depending if you want to work live or offline. And then those data, which contain synchronized capture of different RFkin, will be fed to GMR-RX Live, or there's also a non-live version, that will actually do the packet decoding. So it will look for the sync pattern, acquire the TDMA synchronization, frame number, start decoding the BCCH, lock onto the control channel, and then if it sees any assignment message on the control channel, we'll actually try to see, okay, is that an RFkin that I can receive in the bandwidth that I see? And if yes, we actually jump to that control, to that dedicated channel and start decoding packets for it. And all of these packets are sent through GSM tab to Wireshark, and we've written dissector for Wireshark to decode the packets. That's basically what I've just said.
Can you do something interesting with the channelization? Do you have like a hierarchy or something?
Not really. What it does is, depending on the number of channels that you pull, it's either going to use a PFB or just frequency escalating filters. When you're in kind of discovery mode and you're looking for basically all the RFkin, it will most likely use the PFB. But once you know which channel actually are useful in your area, it's best to just use frequency escalating filter for the like 5 or 6 frequency that you want to listen to, basically. So Osmocom GMR, it contains through the utility I just talked about. It also contains, what's written is really a library of primitives for GMR1, so it contains a bunch of stuff for sync and modem, and you could write other GMR1 application, including possibly a base station if you wanted to, because if there's a demodulation, there is the equivalent modulation. If there is a channel decoding, there is the equivalent channel encoder and stuff like that. Yeah, as I mentioned, the codec was different, so it also got reverse engineered, and I rewrote an open source version, and there is a GMR1 AMB decode so that if you're recording of audio, you can actually play it out. Yeah, the packet parsing, as I said. The dissector we wrote are not complete. Any message that, since it's heavily based on GSM, we can forward a bunch of the packet just to the GSM dissector, which is nice. But some of the BCCH packets are not decoded yet, mostly the system information. We've written the sector for the most interesting one. I'll show examples of those. But the specifications are written in CSN1. If you might be more familiar with ASN1, which stands for Abstract Syntax Notation, while CSN1 is Concrete Syntax Notation. And they basically invented another spec to define things. And of course, this thing there's no free tool to parse it. This thing's a nightmare, basically. As I said, I was now first I'm going to show you how to actually do the L-band stuff. So as I said, I'm going to work off captures because I don't have a dish with me. So let me find my USB port here. Here. Oh wow, this is dark. Let's see, what do I have anything? Okay, so the first thing I'm going to do is here there is a utility called GMR1 process recording. Its name is slightly misleading because it doesn't actually process anything yet. But what you can do is just give him the name of a file that has been recorded with Osmocom FFT. And Osmocom FFT, encodes in the file name, the frequency, and the sample rate. And with the frequency and the sample rate, I can actually detect which RFkin I can possibly decode from that recording and the tuning parameters. So I'm just going to take a capture from MEXSAT. Let's go with that one. Thanks. It's a capture actually made by Nate Temple, which is there. And what it does currently is basically just print out the command line that I need to use to channelize it. So I'm going to, I need to include my environment. So here I have all the parameters. I'm going to cheat a little because I know MEXSAT actually only uses RFkin 175 to 181, so I'm just going to limit it to the interesting ones. Of course. And here, since there is a few channels, it's going to use the rational resampler. Here I'm processing to file. That's something I should have mentioned. GMR1 3G is currently experimental. And the live version of the decoder doesn't actually support it yet. I need to work it, so I need to work off files, basically. So here it's saved in my /tmp, which is the default place where it plays them, the channelized version. Then I can take the GMR1 RX utility. The first parameter is the number of samples per symbol, which is 4 in this case. And I can tell him to process RFKN 178, for instance. I should have, I don't. Well, I'm going to start Wireshark. So as I said, all the packets are sent to GSM tab, so you can just use Wireshark, listen on your loop back. Here. Launch the RX, it will do a bunch of stuff, and if you go into Wireshark, you'll find a bunch of decoded packets. And each time you have the, so for example, I said, that there's a tight integration with GPS. Well, here it provides, the GPS almanac and the war number and stuff like that. The most interesting information in the broadcast are found in the System Information 3A, here, segment 3A, because it will actually tell you first which network you're on, which include the MCC and MNC. So if you look at the mobile country code for 334, it's Mexico, so I know I'm listening to the right satellite. It will actually also tell you the current position of the satellite if you want to point your dish better. and it will tell you this beam where it's centered, basically. And so you can scan all the channels that you can find. That's what we've done. And these, for instance, are the position of the satellite beams from MEXSAT we've actually been able to receive from California in this case. I haven't actually processed the beams from Nate's capture yet. As I said, we don't actually have any traffic from MEXSAT yet, so I'm gonna load another capture, which is a capture that I made a while ago at home that actually has some traffic in it. Let me restart the capture here. And if I process 267, TNT call 267. So here I'm basically giving it several files at once, and I just prefix the file with which RFCAN it is. So here I'm telling it that this file actually is containing data for RFCAN 267, and this one is containing data for RFCAN 268, so that it knows that, you know, if there is an assignment going to 268, it can follow it onto there. 268, process the file. So now if we find, for instance, segment 3A, we can find that it's not the same network. Now it's 9015, which is Thuraya. There is the beam center. If you look that up, that's going to be somewhere near Belgium. Yeah, it should be in Belgium, at least. But more interestingly, we can start looking at assignment messages. Okay, so here we find immediate assignment. And we can see that it assigned a channel. You can see the channel description. It's been assigned onto RX time slot 1, ATX time slot 2, RFCAN 268. Good, I have data. And the channel is a traffic channel type 3. So now we can filter and get all the data for RFCAN 268. And then we can get the actual traffic data that's been included, and there is a bunch of basically nothing at the beginning, just because it's the satellite. The core network starts sending data before the phone can possibly receive them, but we get them. And then you can get actual, you know, message like the authentication request, then the ciphering mode command that will actually enable encryption. And you can see that in the ciphering mode command, they transmit the name of the country, and that's supposed to be displayed on the phone. And why do they do it there? Well, just because it's a convenient place, basically, to put data. And so they just modify the commands to suit the need. You've got the call setup. Here it says it's invalid because I actually redacted my phone number out of the capture. But channel mode modify, it goes to speech. And the speech isn't actually displayed here, but if we go and we look, it's saved. It saved this, which is A and B data, and we can process that. GMR1 A and B decode. GMR1 speech dots that. And we save that in the WAV file, and then yeah, replay it if I remove the mute on my laptop. Yeah, it's just me speaking French and trying the DTMF decoding.
That's pretty cool.
So that's pretty much it for how to receive data in L-band. I wanted to talk to just mention C-band in the. So in C-band, mostly what we've started looking at it with much more advanced setup. Unfortunately, the hard part is that all the synchronization patterns, you don't find them on C-band because C-band is designed to be received by the ground station, and the ground station is the timing master, so it doesn't need timing information. So following the TDMA pattern on C-band is not easy, but you can find the RACH messages, and as I said, they contain GPS information, and so you can actually just collect them and plot them. And that's like a 8-hour capture of like the phone call that have happened on Thuraya. Since there's only 2 satellites, you can pretty much we observe only one, but we get like half of the traffic basically. And it's interesting. Yeah, there is some interesting, like if you look in Europe, you won't find many points except outside, the sea, obviously, because we have a good coverage. Except in Italy, like there are apparently no idea why. If you look in India, you don't find many points at all because it's actually illegal to. Thuraya is actually illegal in India. So the few people that actually placed phone call there,
Why is it illegal?
I don't know. Just go ask the Indian government. And I mean, you can also correlate it with like. I don't actually know how to go to. Oh, yeah, satellite. Most often, the points will actually correlate with actual geographical features, because people are not just in the middle of the desert; they're actually, in cities. And I mean, by cities, I mean like small patches of people. Yeah, the code for the C-band analysis is also in the repo. It just requires a more complicated setup basically. But if you were interested into running it, I can definitely help you there as well.
Can you give us a very quick summary of what you need to do that?
To receive a C-band, you need a C-band dish and point it at Thuraya. The only thing is that the C-band signal is sort of focused onto the main station, which is in Abu Dhabi. No, wait, no. How is that? Oh man, the tallest building in the world. Where is that?
Dubai.
Dubai. It's near Dubai, and they have very large disks with very good meteor condition, which means the signal that they send is not very strong if you're not basically close to there. So we've been using, Dimitri has been using a relatively small dish of like 1 meter and something, and he actually managed to get some pretty good signals. We have somebody that's helping us, which is in Norway with a 3-meter dish, but at that point, we can only get coverage for like 8 hours, because when you have a large dish, it needs to be tracking, because the satellite is on a slightly inclined orbit. They do that to save fuel, I think. But yeah, I mean, if you have a dish and a good LNB, there are pretty cheap LNB, PLL. You need a PLL LNB because the channels are very narrowband, so like TV LNB don't work. But there are no cheap LNB on eBay for like $50 or something that are pretty good. But yeah, if you have that setup, you can actually run it pretty easily. So yeah, that's a couple of interesting resources. So obviously the project website, the specification are interesting. If you want more detail, I did 2 talks at 3C3 about them. One focused on introduction, so it's not really useful because I mostly cover the same material, except maybe a little more in the higher layer. But something that might be more interesting if you want more detail is the 31C3 talk, which talks about reversing the voice codec and cracking the encryption. I'd like to thank a few people, mostly Dimitri, USA Satcom, and Nate Temple, for providing data from around the world and basically running a lot of the capture and testing the stuff for me. And thank you, of course, for being here, and Balink for having me.
Thank you. That's amazing. Really, really cool stuff. Anybody got any questions? Must have one question. Here we go.
I know I have a question for everyone. Have you decoded high penetration alerting messages, and do they have a different PHY?
Yes, they have a different PHY. They use 8 PSK. We haven't actually demodulated any of them yet because they really they don't carry more information than you find on the paging channel, basically. The only thing that's going to tell you is, we're trying to page that IMSI, but the same information is also in the control channel in the paging messages, basically. So we didn't really. Especially since they're using a different modulation, so we would have to write a completely other demodulator just for that.
So is that right? The GPS location is actually sent from the MS to the satellite, not the other way around. So the satellite doesn't actually know where the handset is, it just believes what the handset says, right?
I mean, the GPS position is sent from the terminal to the satellite, right? Yeah. But the satellite also knows in which spot beam you've transmitted. And if you actually try to place a phone call reporting one position and using a spot beam of another country, they're actually going to tell you, no, please go to that other spot beam and then retry.
Okay.
Yeah.
So no free phone codes for cheaper phone codes?
No, but I mean, you can totally fake your GPS position. Yeah. The phone firmware, they've been nice enough to leave the debug symbol in there. So.
All right, any other questions? All right, let's thank Sylvain one more time. So I realized that I did actually get a little bit late here. So I think we'll wrap it up for tonight. We had Chris on the docket, but since he's a local in the Bay Area and we have a scheduled meetup next month, Chris is actually going to very graciously postpone his presentation tonight and present next time when I think there'll be a little bit more time and he's going to cook up an extra few cool things to show us as well. So thank you for graciously doing that. But we'll wrap up there tonight. I think it's been a pretty good night. Thank you all very much for coming and consuming lots of pizza. That's great. Hope you enjoyed it. And, thank you. No worries. Thank you. And yeah, keep hacking away. See you tomorrow at the GNURadio Hack Day. It should be fun. So let's do one more round of applause for our speakers tonight. All right, so see you next month, early October, right? October 5th. See you then. Good night.